Okay, so your boss says to make a super thick anti-reflection coating out of magnesium fluoride on glass because it's cheap or something. And we're going to see why that may be a bad idea. So first of all, let's just draw it real quick. So we've got glass here, n equals 1.5. We've got magnesium fluoride film on it, and this is air. And light is going to come in, and some's going to bounce off the top, and some's going to go down and bounce off the bottom of the film. And we want these two to be destructive interference, because that's what keeps you from seeing a reflection. So part A, the question is, I forgot, what was the question? What order is your boss trying to use? What order? What you'd have to do is just start writing the thin film anti-reflection coating equation. And you know me, I like to just go with the general ones. So the phase difference between these two waves, remember it depends on the path difference. So 2 pi times the path difference, which is 2t, because it goes down and up. All right, so this is t, whatever that is, 2t over then the wavelength in the medium. So that's the lambda over 1.38, because it's 1.38 in the medium, plus the difference in phase. So this one sees a pi phase shift because it's from low index to high index. And this one sees a pi phase shift because it's from low index to high index. So it's plus the difference in phase, pi minus pi. So there is no difference in phase. They both went through a pi phase shift. And we want it to be destructive. So we'll say maybe m plus 1/2 times 2 pi. That way for m equals 0, you've got pi. M equals 1, you got 3 pi, etc. So we then say what order? Well, let's see. This is 0, so the 2 pi's can go away. We have the thickness, we can plug that in. What order? We can just solve for m and then hope it comes out as an integer or something's gone wrong. We don't know the wavelength, but you have to think, what does an interference, what does an anti-reflection coating do? It takes reflection to 0 for one wavelength, but remember you want to put that in the middle of the visible. So we actually know, since the problem says we're an anti-reflection specialist, we know that that's 550 nanometers in the middle of the visible. So let's start putting in numbers. We have 2 times 498 nanometers times 1.38 over 550 nanometers. All right, equals m plus 1/2. So you solve this, and it's 2.5. Basically, the nanometers cancel. It's unitless. It's 2.5, and then you bring this over, and you find m equals 2. So your boss is trying to use the m equals 2 order. Now, technically, that's the third order, because 0th order is the thinnest film you can get. A little thicker, and then a little even thicker would be m equals 2. But I think when we grade it, we're really just looking for the value of m. We're not going to get into the semantics of the order number. Let's see, part B says, basically, why is this maybe a bad idea? And for that, you want to think about where are the maxima? Where's the constructive interference? At what wavelengths will there be constructive interference? Well, to find that, let's just set that up again. We want 2 pi times the path difference, 2t, over the wavelength in the medium. Okay. Plus the phase difference. But we're still talking about the 2 rays that come out, that bounce out. So it's still the same. It's still pi minus pi. Just because we're doing constructive doesn't make a difference. All right, that equals. And now, instead of having it be some half wave difference, we want it to be a full wave difference. So 2 pi times m. All right, so again, the 2 pi's go away. And pretty much you can sit here and find the constructive ones by plugging in all the numbers and solving for lambda as a function of m. Now, lambda is not necessarily 550 here, because now we're not talking about where you want to put the destructive interference. You're talking about where does the constructive interference occur. So let's see, we could spin this around, and when I did, basically just lambda goes here and m comes over here. It's really 2 times t times 1.38. So that's 1374.5 nanometers divided by m. and those are your lambdas for different orders. And they're all going to happen. Just because this was designed at m equals 2 doesn't mean it only has physical effects at m equals 2. All the orders will occur, so let's calculate the lambda for all the orders. M equals 0 in this case doesn't make sense. M equals 0 would be lambda's infinity. So that we don't have m equals 0 for this one. We have m equals 1 though, and for that, lambda equals 1374.5 nanometers. This divided by 1, and that's in the infrared. The near infrared, really. But that's fine. If your anti-reflection coating reflects some infrared light, who cares? Because you can't see it. So we're assuming this is of interest for visible applications. M equals 2. Lambda, divide that number by 2, and you get 687 nanometers. Uh-oh, that's a problem, because that's in the visible. So making this thing thicker collapses the spectrum a little bit, and instead of the constructive interference being outside the visible, now this one showed up inside the visible. What about m equals 3? Lambda, just divided by 3, is 458 nanometers. Also in the visible. And then finally we could do lambda 4, or m equals 4, and we're going to get pretty much half of that one, 343 nanometers. And that's in the UV, so that would be okay. So the problem with going with a higher order, thicker film is that that causes you to get some maxima in the visible, not just having the minima, but due to the destructive interference. So tell your boss it's a bad idea. Unless he's into purple.